Welcome back to Calculus 3. And in this part, we are still in section 2.7 about cylindrical and spherical coordinates. And mostly, I just will walk through very quickly the general idea and some examples on the textbook. As you can tell, this is really our textbook. Okay, cylindrical coordinates, it is a simple extension from polar coordinates or theta and z. And also I tried to explain in my other video how do you choose angle theta. Angle theta really it depends the x and the y, and usually if you could just plot x and y in the two-dimensional plane, then hopefully you will see how the angle would look like. Okay. Then spherical coordinates, it's more complicated. Spherical coordinates, basically you will have to, well, I'm trying to find out the graph. I believe there's a graph on the textbook. Show the idea how the spherical coordinates works. Yeah, this is what I'm looking for. Spherical coordinates here, okay. Spherical coordinates, it has a rho, theta, and a phi. Rho, it is the distance from the point to the origin. Phi, it is the angle from the axis to the line segment rho here. And then theta, actually, it is carried from the cylindrical coordinates. Okay, and also we don't have R explicitly. It really would be very helpful if you see R in the spherical coordinates, because in the spherical coordinates, R really can be considered as it is the line segment opposite to this angle phi could be on the top there. Okay, so R, it is rho times sine phi, or it is rho times sine phi. Accordingly, you have these conversion formulas. And also the textbook just showed as just explained. Or it is rho times sine phi. If you realize this part, it will make the conversion formula a lot easier. I mean, between rectangular and the cylindrical, okay. Between rectangular and the spherical. And maybe we can take a quick look about the examples of the textbook. I say, yeah. This is the example I'm looking for. I think there's not a lot to say about this example here. Checkpoint 258, it's also done on my other video. And maybe we can take a look converting. Yeah, maybe take a look at converting from rectangular to polar to spherical coordinates. Okay, to both, maybe to both. So we are having -1, +1 to square root of 6, and then we want to convert to spherical and to cylindrical. I would say in general it might be easier to convert to cylindrical first. Let's take a look at how the textbook does this. Show solution. Actually, it is, yeah, actually somewhat the textbook got this mixed. Okay. Rho, it is x squared plus y squared plus z squared. So rho, it is square root of 8, which is 2 times square root of 2. Remember, theta, it is always given in the fashion of y over x. You want to be very careful. It is y over x, it is -1. And in this case, it's true. -1, arctangent of -1 is 3 pi over 4. But anyway, you want to be very careful. Let me check if the textbook didn't even not give a graph. I mean, if you have x and y values switched, the angle will be totally different. Okay, the angle will be totally different. And then we have rho, theta, and phi. Phi, it is always the arc cosine or cosine inverse of z over rho. Rho, it is already calculated. Z, it is we have z here, x squared plus y squared. Z is square root of 6. Z is square root of 6. Okay. Z is rho times cosine phi. So z is square root of 6. And so what we are having here is a cosine phi. It is z over rho, right? Square root of 6 over 2 times square root of 2. So it turns out to be square root of 3 over 2. And then finally, we do have the spherical coordinates for the point. 2 times square root of 2 rho, theta, and phi. And if you need to have the cylindrical coordinates, or you could follow the way on the textbook, but anyway, I say it would be a lot easier if you start from the polar coordinates. So that's the square root of 2. The issue about theta. Actually, theta, because this textbook didn't do spherical coordinate first, so you can get the answer from spherical coordinate directly. And also, if you watched my other video, I'm saying this theta really should be calculated and observed from the drawing. Okay, so that is r, theta, and z. Z, it is the same as given. We are having the ordered pair x, y, z in the rectangular fashion, and we converted this rectangle to both spherical and cylindrical. And mostly, actually, this is the bigger part. I just want to explain briefly how do we understand the meaning of cylindrical and spherical coordinates. So this is example 2.65. Describe the surfaces with the given spherical equations. We are having theta equals pi over 3. Theta equals pi over 3. It says describe the surface. Can you imagine theta equals pi over 3 as a surface? Okay, let's click on the solution. Theta as a surface, remember theta is the angle from the x-axis to the r. R, it is the distance, the line segment of the distance from the projected actual point, in the xy plane from here to the origin. So that's theta. When theta is a constant, which really means what we are having here, it is a plane passing through the z-axis, okay, such that the angle going back to x-axis or to the xz plane, it is pi over 3. Theta equals pi over 3, it is a surface like the blue panel here, okay, surface. How about equation phi equals 5 pi over 6. They are all from spherical coordinates. Theta equals pi over 3, that's a plane. Would you imagine phi equals 5 pi over 6, that's another plane? Well, if you think that's another plane, then you especially want to pay attention, take a look how the graph would look like. It is a cone-shaped surface, right? Cone-shaped surface opening upward. Remember, phi, it is always the angle from the axis to the line segment. So when phi stays as a constant, you can consider the line segment rotating around the z-axis. So that is how the cone-shaped surface is formed. So phi equals 5 pi over 6, which really forms a cone-shaped surface like shown here. And then what do you imagine when rho equals 6? Rho equals 6, remember, rho, it is the actual distance from the point to the origin in the space. And what kind of surface such that the distance from the point to the origin will stay at a constant? I'm seeing that's a sphere, right? So if you have any confusion, this is how the sphere would look like. So it is centered at the origin, radius 6. radius 6. I think that is the material of section 2.7 I want to cover, and thank you for watching.